welcome to this new lecture. So I'll just briefly review what we did last time. So basically we were continuing our discussion on defect equilibria in non-stoichiometric materials, and following from what we discussed in lecture 7, we discussed for example in case of oxygen deficient oxide, when you have simultaneous presence of oxygen vacancies as well as metal interstitials, in that case what happens. And then we worked out expressions of reaction constants for the reaction for vacancy formation and reaction for metal interstitial formation, and then looked at the electrical neutrality conditions, followed by for two limiting cases. Case 1, when oxygen vacancy concentration is much larger than interstitial concentration, metal interstitial concentration. In such a case we worked out what is the concentration of VO, and in such a case since VO is much larger than MI, the electron concentration is now dependent upon VO concentration. It is determined by VO concentration. As a result, MI or metal interstitial concentration expression has N, and this N comes from the expression of VO. So as a result, VO has a dependence of PO to the power minus 1 by 6, while MI has a dependence of PO to the power minus 1 by 3. And then we also worked out what is the partial pressure of oxygen at which this is going to happen. Similarly, we took another case when MI is much larger than VO, and following the similar procedure, we worked out the VO and MI concentrations which have dependence of minus 1 by 3 and plus 1 by 6, and of course the boundary of partial pressure remains same, which means that partial pressure of oxygen has to be much smaller than K2 by K1 square for this region. So we constructed on this basis a diagram, a plot of concentration of defects versus partial pressure of oxygen, where we clearly see how the defect concentrations vary as a function of oxygen partial pressure. And then we looked at the defect equilibrium in metal deficient oxides when metal vacancies dominate, and following the similar protocol as we followed in case of oxygen deficient oxides, we worked out what is the relation of metal vacancies and resulting holes with respect to partial pressure of oxygen, and I left it to you as an exercise to work out this defect equilibria when oxygen interstitials dominate, and what happens when you have mixed presence of oxygen interstitials and metal vacancies. The derivation would be similar to what we did in case of oxygen deficient oxide. And then finally we looked at what is the equilibria in case of intrinsic ionization. In intrinsic ionization, the K value is equal to electron and hole concentration product, and which is independent of partial pressure of oxygen. And then we started working on developing equilibrium concentration diagram as a function of partial pressure of oxygen. There are three conditions which we are considering. One is low partial pressure of oxygen, which means you have deficiency of oxygen. Another is high partial pressure of oxygen, which means excess of oxygen, and then you have moderate or intermediate oxygen partial pressures when oxide happens to be stoichiometric. And the defects which are present as under these conditions are either oxygen vacancies or oxygen interstitials. The type of defects that are present will depend upon things like what is the crystal structure of materials, etc., and what sort of stoichiometric defect does the material prefer. And suppose you have a material which prefers Schottky defect in the stoichiometric condition, which means you have vacancies of metal and oxygen, which means that the concentration of these defects also follow in higher and lower pressure regime. In that case, you will not have interstitials, but you will have vacancies as dominant defects. So in this case, we have taken material to have Frankel defect. So this is MO having Frankel defects. Frankel defects of anion, which means it would be anti-Frankel disorder. As a result, the dominating defects that would be present at either pressures would be VO or OI. So, now we write the defect reactions. For low PO2, it is a familiar defect reaction, that oxygen goes out of the system, giving rise to oxygen vacancy, and then we worked out what is the equilibrium constant for this reaction. Then we looked at the high PO2 case, similarly forming oxygen interstitials, and then we looked at the conditions for intermediate PO2. In the case of intermediate partial pressure of oxygen, you can have two conditions. First condition is when you have intrinsic ionization, which is the dominant factor, which means you have intrinsic formation of formation of electrons and holes, and here Ki is equal to product of Ne and NH independent of PO2. Or second scenario is when you have anti-Frankel disorder dominates. As a result, you form oxygen interstitial and oxygen vacancies, and Kf is product of these two defects concentrations, and again is independent of PO2, which we know. And then if you combine these expressions, you can get an equality which is Kf Ki square is equal to Kvo Koi, just as a point of interest. And now we are going to look at the limiting conditions for each of these regions, so that we can work out the defect concentration profiles in each of these three regions, which is low PO2, stoichiometric, intermediate PO2 or high PO2. So, we will start the discussion for this lecture from the, so we will take limiting conditions. Okay. So, we will take the first limiting condition, which is the first condition is when you have low PO2 conditions, that is according to our particular oxide, you have oxygen deficit, that is VO dominates. So, in such a situation, if you look at the defect reaction was OO going out to giving rise to VO and 2 electrons. So, as a result of, so the charge neutrality means VO is equal to half Ne, and these two are much bigger than OI. Okay. So, this is the situation. So, now we can write, we know that what and this reaction was, I can just write the reaction now. So, OO was equal to half O2 VO plus 2E. So, VO for this reaction you can work out yourself, half Ne will be equal to KVO divided by 4 to the power 1 by 3 into PO to the power minus 1 by 6. So, this was the expression for VO. Now, since VO is the dominating defect, as a result, what is the concentration of OI now? Now, the concentration of OI will be governed by the reaction, which by the Frankel disorder reaction. So, now OI will be Kf divided by VO. So, this as a result becomes Kf divided by KVO to the power 1 by 3 into PO to the power minus 1 by 6, and this becomes to equal to Kf into KVO divided by 4 to the power minus 1 by 3 into PO to the power plus 1 by 6. And from the intrinsic ionization reaction you can work out the concentration of holes. So, NH would be Ki divided by Ne. Now, Ne concentration is given by this reaction, which is this particular the equation that we worked out. So, Ki divided by 2 into KVO divided by 4 to the power 1 by 3 multiplied by PO to the power minus plus 1 by 6. This would be the expression for your whole concentration, and which can be further modified into, you can write it as Ki into 2 KVO to the power minus 1 by 3, because these go up, and multiplied by PO to the power 1 by 6. We have got the expressions for VO, OI, Ne and NH in the region of low partial pressure of oxygen. So, what happens here is, again to reiterate, that here VO and Ne concentration, which is oxygen vacancy, and electron concentration is given by this reaction, which is the dominant reaction, and now OI and NH concentration are given by the intrinsic disorder conditions, which is Kf by VO or Ki by Ne. So, these are the conditions for low PO2 region. Now, we have to work out what is the condition of partial pressure of oxygen that will allow this to happen, below which this will happen. So, for that, since VO is much larger than OI, so if you now replace the VO value, which is KVO divided by 4 to the power minus 1 by 3 into PO to the power minus 1 by plus 1 by 3 into this should be plus not minus, much greater than OI, and which is Kf multiplied by KVO divided by 4 to the power minus 1 by 3 into PO to the power plus 1 by 6. So, what you do is that you take this on that side. So, basically it becomes Kf to the power minus 1 into KVO divided by 4 to the power 2 by 3 greater than PO to the power 2 by 6, which is 1 by 3. So, which means basically PO2 is less than your, so you just cube that everything. So, this becomes KVO divided by 4 square multiplied by Kf to the power minus 3, okay, or alternatively it becomes PO2 is much lesser than KVO square divided by 16 Kf cube. So, this is the partial pressure of oxygen, which is smaller than this particular ratio. At these pressures, your conditions VO much larger than OI is going to be valid. So, this is the first limiting condition. Okay. Now, to work out the second limiting condition, let us take high PO2, that is excess oxygen. Now, under these conditions, the requirement is OI is greater than VO. So, the dominant reaction in such a case was half O2 going to OI plus 2H, okay. And the electrical neutrality condition was NH, half NH is equal to OI is much larger than VO. Okay. So now how do we work out OI? Again you follow the similar procedures, we have done it many times now. So I'll just write the expression. So OI is equal to, so reaction constant for this would be KOI. So OI is equal to half NH would be equal to, so KOI would be equal to OI multiplied by NH square divided by PO to the power half, and you make the replacement for NH in terms of OI is equal to 2 OI. So that will become OI square. So what you get, so basically what you get is, so this will be OI NH square divided by PO to the power half. So OI would be your KOI divided by 4 to the power 1 by 3 multiplied by PO to the power plus 1 by 6. So this would be the expression for your OI and OI and NH. So similarly, as compared to the previous case, now VO concentration is now determined by Frankel reaction. So which is Kf divided by, because if it's a dominating condition when PO2 are the when OI is the dominating defect, then VO cannot be created by any other means other than Frankel defect. So but Frankel defect also gives rise to both VO and OI. So the VO concentration will depend upon OI concentration. So Kf divided by OI, and this would be equal to Kf into KVO, Kf into KOI divided by 4 to the power minus 1 by 3 into PO to the power minus 1 by 6. And similarly NE will be equal to KI divided by NE, and NE would be equal to KI divided by NE, and we can write KI divided by NH, just slipping out a little bit. So this should be NH. So KI divided by 2 KOI divided by 4 to the power 1 by 3 into PO to the power 1 by 6, which means NE would be, now you can either take this inside, so you can make it, so this will become KI divided by 2 KOI to the power 1 by 3 into PO to the power minus 1 by 6. So we have got the expressions for OI and NH from the defect reaction, and we have got the concentrations of oxygen vacancy and electron from the Frankel and intrinsic ionization reaction, because that is the only mechanism by which these defects can be created, but the concentration of these will depend upon the concentration of other defects, which is oxygen interstitial and holes. So now what we need to do is that we need to work out what is the limiting condition, and the limiting condition has to be worked out by the condition that OI is much larger than VO. So you just now replace the concentration of OI and VO here, and I will just write the final expression now. So what you will get is, so replace the expressions for VO and OI in the above equality or inequality, the way you look at it, we get PO2 much bigger than 16 Kf cube divided by KOI square. So, now which means the on the higher pressure side PO2 must be larger than this particular value. Now, we will look at the conditions, limiting conditions for the the defect concentrations in the stoichiometric region. So, in the stoichiometric region we have two cases which are possible. So, we can have, so we will just write number 3. Okay. So, in this we will first take case 1. Case 1 is the condition when intrinsic ionization, internal disorder or intrinsic ionization dominates. That is electron and hole creation. So, corresponding concentrations would be here Ne is equal to NH will be equal to Ki to the power half, and these two in this case, since you have this is the dominating phenomena, these two are much larger than both OI and VO. Okay. So, how do you find the concentration of, but you still have some OI and VO present. So, how do we find out the concentration of OI and VO? So, in this case now the concentration of OI and VO are given by, now what are the instances where NH, Ne, OI and VO are related? They are related only in the relations when oxygen vacancy is formed or the oxygen interstitial is formed. So, for VO concentration, VO will be equal to KVO divided by Ki. Now, we know that, let me just write the complete thing. Now, so in the VO reaction, we knew that OO was equal to half O2 multiplied by half O2 plus VO plus 2 electrons. Now, in case of less partial pressure of oxygen, since oxygen vacancy dominates the defect, which means electron concentration is automatically fixed by vacancy concentration. Now, here what we are saying is that Ne and NH concentrations are much larger than OI and VO, which means in this expression now, which is the reaction for formation of vacancy of oxygen, any concentration is no longer governed by VO concentration, rather VO concentration is now governed by any concentration. So, what we will do is that, so this expression was VO was equal to KVO divided by Ne square, okay, multiplied by PO to the power half, all right. So, this would become KVO divided by Ki. Now, Ne is given as Ki to the power half, which means Ne square becomes Ki into PO to the power minus half. So, this is the vacancy concentration in this region, which is the stoichiometric region. Similarly, OI concentration will be given by KOI divided by PO to the power half multiplied by, just a second, because we had KOI was equal to PO to the power half divided by OI into NH square. So, OI will be equal to, oh no, so KOI was equal to OI into NH divided by H square. So, OI now will be equal to KOI multiplied by PO to the power half divided by NH square. So, this becomes KOI divided by KI into PO to the power plus half. So, in this region the VO and OI concentrations will be lower than NE and NH concentrations, but they will change as PO to the power minus half in case of VOO oxygen vacancy, or PO to the power plus half in case of oxygen interstitials. Okay. So, this is the case 1 when when your internal ionization dominates. Now, case 2 can be when anti-Frenkel disorder dominates, which means OI is equal to VO is equal to Kf to the power half, much larger than both Ne and NH. So, that is the case under stoichiometric condition. So, now since OI and VO are independent of partial pressure of oxygen, which means in the defect reactions. So, now I have to work out what is Ne and NH. So, I know that for KVO I had VO multiplied by Ne square multiplied by PO to the power half. Okay. And for KOI I had OI multiplied by NH square divided by PO to the power half. So, now since OI and VO are independent of partial pressure of oxygen, but Ne now is much smaller than, or NH is much smaller than these two will be dependent on. So, as a result, now Ne will be equal to KVO to the power half divided by concentration of VO, which is Kf to the power half, and this will now become Kf to the power 1 by 4, and this will be PO to the power minus 1 by 4. So, this becomes KVO to the power half divided by Kf to the power 1 by 4, or KVO square divided by Kf to the power 1 by 4, that can also be written. So, basically you write it as KVO divided by Kf. So, this becomes to the power 1 by 4 into PO to the power minus 1 by 4, and similarly NH will be equal to KOI to the power 1 by 2 divided by into PO to the power 1 by 4 divided by concentration of OI, which is Kf to the power 1 by 4. So, this becomes KOI square divided by Kf to the power 1 by 4 into PO to the power 1 by 4. So, we have established these two conditions for stoichiometric condition. So, now we have complete picture. We have determined the concentration of defects for the region when partial pressure of oxygen is low. We have also determined the limiting condition of oxygen partial pressure below which this is going to happen. We have also established the condition of concentrations for the region when oxygen partial pressure is high, as well as we have also worked out what is the limiting condition of that high partial pressure of oxygen. And between those two ends of partial pressure of oxygen, we will have stoichiometric region, in which case 1 when internal disorder dominates and case 2 when anti-Frenkel disorder dominates. So, now what we will do is that we will now combine these and make the plots. So, now combine the above 3 regions with 2 cases for stoichiometric condition, and this will give rise to concentration versus PO2 diagram at a fixed temperature, and this will give you what is called as Brewer's diagrams. These are very important diagrams in case of ceramics to work out what is the defect concentration as a function of partial pressure of oxygen. So, we'll look at the first case. So, we'll look at the first case, case 1, when internal disorder dominates, that is Ne is equal to Nh, much bigger than Vo and Oi. So, what we will do that, we will just make these lines. Let us say this is log of PO2 and this is log of concentration, and that would mean Vo, Oi, Ne or Nh. Okay. So, first I will mark what are the limiting conditions. So, this is the boundary condition, this is a limiting condition. So, this would be low PO2, this would be high, and this would be intermediate PO2. Okay. So, the conditions that we worked out were oxygen partial pressure. So, if I go to some earlier slides, okay. So, this was the first condition, KVO divided by 60, KVO square divided by 16 KF cube. So, this boundary will mark, so this boundary would be KVO square divided by 16 KF cube. Now, since K depends upon the temperature, this boundary will shift as a function of temperature. So, we are considering this exercise at a constant temperature, and now we will look at what is the condition for other, which is 16 KF cube divided by KOI square. So, this would be 16 KF cube divided by KOI square. Okay. So, these are two boundary conditions. Now, in the first region, we knew when we had this internal disorder which dominates, we know that in this condition, in the center, Ne was equal to Nh. Let us start at some arbitrary concentration, which will be dependent now on only temperature, that we can calculate by just knowing what is the band gap of the material. Now, we know that Nh varies at higher pressures. If you now go back to previous slides, what we can see is that Nh varies as a function of PO to the power. So, this is Nh is proportional to PO to the power plus 1 by 6. And how it varies in the lower pressure side? It varies as minus 1 by 6. So, this is again Nh. Okay. Now, in the what about Ne? So, Ne goes as in the higher pressure side as again minus 1 by 6, this would be sorry plus 1 by 6, I am sorry. So, Ne in this region would vary as minus 1 by 6, it would also vary as minus 1 by 6 in this region. this would be NE. What about VO and OI? We know that OI is half of NH in this region. So, this would be OI is equal to half of NH, and let me use a different color here. I don't want to confuse it. So, I'll choose a different color. So, this would be OI. In the lower pressure region, I will have VO is equal to, again we will use a different color here as well. So, this would be my half of NE. Okay. So, now we have drawn the concentrations of 3 defects on each side. Now, what about how do they vary now? Now, we know that in the center region both VO, the VO decreases at minus half PO2, PO to the power minus half, and OI increases as PO to the power plus half. So, the slope will change here. So, this will become like this. So, this will be your VO and this will vary at minus half, and again it continues to vary as minus 1/6 in the higher pressure region. And so, VO varies as minus 1 by PO to the power minus 1/6 in the high pressure region. I will just draw this line which somehow got erased. Okay. So, now we will see what happens with OI. OI again varies in the intermediate pressure range as plus half. So, this point of intersection would be parallel somewhere here. So, this goes as plus half, and again it goes as minus plus 1/6 in the low pressure region. Okay. So, I am just putting the right square brackets around everything so that everything is correct. So, this is how you will plot the concentrations of each of them, because the moment you draw one of them, then you get the lead to draw others into other regions. So, first we do NE is equal to NH in the central region, which is the stoichiometric region, because we knew that it's like this, and then from the ends of NE and NH you follow NE and NH plots according to the equations that you have worked out in the previous slides, and then VO